In this session, we are going to study about the block diagram reduction and signal flow graph. Now, before going to this block diagram reduction part, we need to understand what is a Laplace transformation and what is its importance in the control engineering. Now, Laplace transformation generally it is some sort of a calculus part is involved and some sort of algebraic part is involved in this. Now, it is a technique which is talking about the function here. Function, maybe we can say it is a function of time. That is like in engineering, we talk about the time here. In engineering, we talk about the time. Like let us say for an electrical engineer or in an electrical engineering, we talk about the signals which consist of amplitude and the time. Let us say in a sine wave, we have the amplitude in y-axis and time in x-axis there. Right. Now, in Laplace transformation, it talks about the function of time and the transformation, and it transfer it's into a new function here. New function we call like we can take the transformation of time domain into some another domain. Let us say that time domain as the S domain here. Right. It is the new way of representing or assigning a function here. Laplace transformation let you to solve the different types of differential equation in an original way. Let us say here you can see the Laplace transformation is very useful in solving intergo differential equation here. Right, that means let us assume for solving a differential equation we have variety of methods depending upon the question what it is asked here. It might be in the form of separation of variable partial differential equation, Bernoulli's equation, or first order linear differential equation, right, or variation of parameters. These are some of the examples what we use to solve the differential equation. But here in Laplace transformation, these things has a unique way of solving the equation here. Now, the Laplace transformation is defined as the transformation technique relating time domain function to the frequency dependent function of complex variable. This is called as the Laplace transformation technique here. This is the Laplace transformation technique. Right. Now, where we use this Laplace transformation? Laplace transformation, it is a time dependent here. Sorry. Now, the Laplace transformation is very useful in solving intergo differential equation, that is the integral equation and the differential equation. The concept of the Laplace transformation, which is the heart of control system analysis, is based on Laplace transformation here. Now, the definition says like this: the transformation technique relating time domain function to frequency dependent function of a complex variable. This is called as a Laplace transformation technique here. Now, we shall take one variable or the one function here, that is f of t. F of t is the function for which the time t should be greater than 0 here. Now, if by the definition I can say f of s, I'll write capital F of s is the Laplace transformation of f of t. Is the Laplace transformation of f of t here. Right. This is how we represent the Laplace transformation here. You can take it as L, as a capital letter L, or this type of this is the type of representation here. Now, this can be written as integration of 0 to infinity f of t into e power minus s t into dt here. This is what the Laplace transformation here. F of s is what? F of s is the Laplace transformation of f of t here. f of s is the Laplace transformation of f of t here. Right. Now we have introduced one more variable, that is small letter s. This is the small letter s here, which appears in f of s. This is appears in the f of s here. This is called the frequency dependent complex variable here. This is the frequency dependent complex variable. Frequency dependent complex variable. Right. Now s, I can write s is equals to sigma plus j omega. Right. J is the sigma plus j omega here. J is the imaginary part that is in y-axis here. Right. This is the imaginary part in the y-axis. Now s, we already told it is a frequency dependent complex variable, and we have introduced two terms, that is sigma and omega. Right. We have introduced two terms, sigma and omega here. This is the real part. Right. This is the real part of complex variable s, and this is the imaginary part of complex variable s here. Right. Now this is the Laplace transformation. We have the time dependent variable f of t. We have transferred it into a frequency domain. That is the one more form. We have transferred that into Laplace form, and we have calculated it, or we have reduced this formula. Now after doing this, we need to obtain the answer in terms of time domain itself. Right. So what we need to do, we need to take this time dependent function, or the time function f of t is again obtained back from the Laplace transform by the process called inverse Laplace transformation. Right. This is the process called as inverse Laplace transformation. So what I'll do, I'll write L inverse f of t. L inverse f of t here. Right. So this becomes L inverse of L into f of t. L inverse of L into f of t. At the end, I'll obtain this in terms of f of t itself. Right. So this is how we obtain. First, we have the time dependent function, and that is transferred into a frequency dependent complex variable, that is s, and we do that transformation there, and that is again transferred back with the help of inverse Laplace transformation and obtain the transformation, that is in terms of time dependent variable. The time function f of t and its transform and its Laplace transform f of s is called as the transfer pair. This is called as a transfer pair here. Right. Now we need to understand what is a transfer function. Right. We got to know what is Laplace transformation. Now we need to study about the transfer function. Right. The transfer function of a linear time invariant system is defined as the ratio of Laplace transformation of output to the Laplace transformation of input, under the assumption that all the initial conditions are set to 0 here. Now we have the process g of t. This is the process here, or the plant here. I shall take this as the plant here. We give the input to the plant as r of t. We give input to the plant as r of t, and output from the plant is taken as c of t here. Output of the plant is taken as c of t. This is in terms of time domain. This is in terms of time domain. This is in terms of time domain, but we cannot here the transfer function is a linear time invariant system is defined as ratio of Laplace transform of output variable to the Laplace transformation of the input variable here. But here the question is given, or the system we have in terms of time domain, that needs to be converted into a Laplace domain. Now the Laplace domain of plant, which is g of t, I'll write this as g of s here. G of s is the plant or the process what we have here in the Laplace domain. Now for this we have the input as r of s and we have the output as c of s. Right. By the definition what we have, the transfer function is defined as the ratio of Laplace transformation of output variable to the Laplace transformation of input variable. Right. Now transfer function I'll write as TF. It is a ratio of Laplace transformation of output variable. Laplace transformation of output we have in terms of C of S here. It is C of S is the Laplace transformation of output by the Laplace transformation of input. Right. This is nothing but the G of S. Right. This is the transfer function of any system in terms of the frequency domain or the S domain here, or Laplace transformation what we call here. But for this we have the condition, all initial condition should be 0 here. It should not start from any point, it should be 0 here. Now we shall start about the block diagram reduction part. Before going to this block diagram reduction part, we should understand what is block diagram and how it is represented. To understand that, I have considered one simple example of liquid level control system here. Here in this, what we have here is, we have the pneumatic valve. First we have a tank for which the water should be filled, and we have a controller, we have a float, we have a pneumatic valve here. Now what happens? First, initially when there is no water inside the tank, the water will start flowing from the input here through the pneumatic valve and fills the tank here. So after that, for a certain height, when a certain height is reached, the floats indicates or gives the feedback to the controller here, so that the controller controls the pneumatic valve and the valve is being turned off. So the water flowing from the pneumatic valve will be stopped and the desired level is reached here. Now after that, we will take out the water which is collected inside the tank through output here. When the water is drained off from the tank, the floats comes down, so that the changes will be controlled by the controller to operate the pneumatic valve, and the water start flowing from the overhead tank to the tank which is fitted here. Right. Now this float position what we have is nothing but the feedback here. Right. We have the float position, we have the feedback here. That means the forward path will be the water which is coming inside the to the tank through. First it will comes to the controller, then the controller controls the pneumatic valve so that it fills the water inside the tank here. Right. Now first thing, I shall write this as the first I'll write this one as the controller here. This is one block which represent a system or a plant here. From controller, first we will be giving the input here. First we will be giving the input here. Input is the desired level here. Desired level is the input here what we have. that is given to the controller here. This controller controls the pneumatic valve here. This controller controls the pneumatic valve or operates the pneumatic valve what we have. Then that fills that pneumatic valve, water which is coming from the pneumatic valve will fills up the tank. That fills up the tank here. This is the forward path. Right. Then we will take out the output here, or this is the output here. Output is nothing but the actual level. Is the output here. But we have the float. When the water is drained off from the tank, we have the float which gives the feedback to the controller here or the input here. So we will be taking out the feedback from the output, that is the float position here. This is the feedback which is taken from the output and it is given to the input here, and it is given to the input here, right. I'll represent this output which is given from the the thing which is given to the input is represented by the summing point here. This point is the summing point here. I'll write it down. This is the summing point here. And this point what we have is nothing but the takeoff point here. Now, with this, the physical system what we have is now represented in the form of the blocks, right. In short, we can write any block diagram consists of 5 elements which is associated with it. First one are the blocks. Here you can see first one are the controller, pneumatic valve, tank and the float position. These are the blocks what we have. Right. Next, this blocks is represented in the form of a transfer function that is represented inside the block. Here inside the controller, I'll write in some sort of C of S here, that is the controller, or what I can write, right. Next we have is the summing point, right. That means where the two signals are added up. This is the summing point what we have there. Here the two signals are added up here. Next we have the takeoff point where the signal is taken from the output or signal has been extracted from the path. And fifth one we have is the arrows. Fifth one what we have is the arrows here. This summing point is also called as an error detector here. Right. Now what is a block diagram? A block diagram of a system is a pictorial representation of a function performed by each component and of a flow signal, right. This is what we call it as a block diagram here. And then we can see we have the arrows here. The arrow heading the point towards the block indicates the signal is given to the block, right. Signal is given to the block or input signal, and arrow which is coming out from the block or the away from the block represent the output signal here. And also we can notice, or we should notice, that signal can pass only in one direction and it cannot pass through the other direction. Here, when the arrow mark is represented in one direction, the signal can only passes from left to right, but it cannot passes from right to left. Thus, the block diagram of a control system shows a unilateral property. This property is called as an unilateral property here.